History of composite materials. The chronological narrative of human civilization is conventionally demarcated by the dominance of singular monolithic materials. We speak of the Stone Age, the Bronze Age, and the Iron Age, creating a historical framework that emphasizes the extraction and purification of homogeneous substances. This perspective, while useful for broad categorization, obscures a parallel and perhaps more sophisticated lineage of technological development, the history of composite materials. From the earliest Neolithic settlements to the high-altitude theaters of the Second World War, humanity has intuitively understood and exploited a fundamental principle of mechanics, that the combination of two dissimilar materials can produce a third substance with properties vastly superior to the sum of its parts. The first part of this review undertakes an exhaustive reconstruction of this history, tracing the genealogy of composite engineering from approximately 4000 BCE to 1950 CE. It posits that the modern composite age is not a sudden 20th century phenomenon born of synthetic chemistry, but rather the industrial culmination of a 6-millennium quest to overcome the inherent limitations of natural raw materials. We will examine how the scarcity of timber in the Nile Valley forced Egyptian artisans to invent the precursor to plywood, how the biomechanical demands of steppe warfare necessitated the horn-sinew-wood laminate of the Mongol bow, and how the electromagnetic requirements of radar systems in the 1940s catalyzed the marriage of glass fibers and polyester resins. The analysis is structured not merely as a catalog of inventions, but as an investigation into the mechanical and chemical insights of our ancestors. We will explore the crack-stopping physics of straw-reinforced mub, the hysteresis properties of keratin in horn, and the dielectric stability of early fiberglass. By weaving together archaeological evidence, chemical analysis, and historical records, we reveal a continuous thread of material innovation, a persistent desire to engineer the perfect solid that connects the mud brick builder of antiquity to the aerospace engineer of the mid-20th century. Earth itself, the structural mechanics of Wattle and Daub. In the search for the primordial composite, one must look to the walls of the earliest human dwellings. Wattle and Daub, a construction technique found across the globe from the Neolithic period to the present day, represents the first truly engineered structural composite. While often dismissed in popular imagination as a crude assembly of sticks and mud, a rigorous mechanical analysis reveals it to be a sophisticated system that perfectly balances tensile and compressive forces, utilizing a reinforced matrix design that predates modern fiber-reinforced concrete by thousands of years. At the heart of the Wattle and Daub system lies the wattle, which functions as the tensile reinforcement component of the composite. In structural terms, the wattle is a lattice designed to span the voids between the primary load-bearing timbers of a building's frame. This lattice is constructed from two distinct elements, the staves and the withies. The staves are vertical members, often made of split oak or other durable hardwoods, which are set into holes or grooves in the timber frame. These act as the primary armature for the panel. Woven around these staves are the withies, flexible green saplings or strips of wood, typically hazel, willow, or ash. The weaving process is not merely decorative. It creates a textured three-dimensional surface with significant surface area. This mechanical interlocking is crucial. Just as the ridges on a steel rebar allow it to grip the surrounding concrete, the complex geometry of the woven wattle matrix ensures that the mud matrix, the daub, remains firmly adhered to the reinforcement. The weaving process creates a semi-rigid mesh that can flex under wind loads without failing, providing the wall with a degree of tensile elasticity that a solid earthen wall would lack. Archaeological evidence indicates that this reinforcement strategy was highly adaptable. In some regions, the wattle was not woven but arranged as a lattice of vertical and horizontal laths tied together. In others, nails were used to secure the secondary timbers to the frame. A study of ancient construction techniques identified specific geometric types of iron nails, circular and square cross-sections, used as mechanical connectors in these walls. This suggests that builders understood the need for secure mechanical fixation between the composite panel and the structural skeleton of the building. The daub serves as the matrix of the composite, the binder that encases the wattle reinforcement and provides the wall with compressive strength, thermal mass, and weather resistance. While colloquially referred to as mud, historical daub was a carefully formulated composite material in its own right. It was rarely just topsoil. Builders empirically selected subsoils with specific clay contents, often blending them with aggregates and binders to optimize performance. Chemical analysis of historical daub samples reveals a sophisticated understanding of soil mechanics. For instance, a study of 19th-century Tabik Pampango walls, a Philippine variation of Wattle and Daub, utilized X-ray fluorescence, XRF, and thermogravimetric analysis to determine the chemical composition of the matrix. The analysis showed that the daub was not merely dried earth, but a mixture containing a calcitic binder. This presence of calcium carbonate suggests the addition of lime or the use of calcareous soils, which would induce a pozzolanic reaction, a chemical process where the lime reacts with clay minerals in the presence of water to form calcium silicate hydrates. This transforms the daub from a simple dried mud into a hydraulic cement-like material, significantly increasing its hardness and resistance to water degradation. Furthermore, the daub matrix almost always included an aggregate fraction, sand, crushed chalk, or small stones. In modern composite theory, aggregates serve to improve dimensional stability. Pure clay shrinks significantly as it dries, leading to severe cracking. The inclusion of rigid aggregates creates an internal skeleton that resists this shrinkage, ensuring the matrix maintains its structural integrity during the curing process. The final and perhaps most critical component of the daub matrix is the fibrous reinforcement. Builders universally added organic fibers such as straw, hay, animal hair, or dried grass to the mud mixture. The mechanical function of these fibers is identical to that of glass fibers in a modern polymer composite. They act as crack arresters. As the wet daub dries, water evaporates from the clay structure, causing the clay platelets to draw closer together. This volumetric shrinkage generates internal tensile stresses. Since ceramic materials, like dried clay, have very low tensile strength, these stresses inevitably manifest as microcracks. Without reinforcement, a microcrack would propagate rapidly through the brittle matrix, leading to catastrophic failure and crumbling. The organic fibers interrupt this process. When a crack tip encounters a fiber, it must either break the fiber, which requires high energy, or pull the fiber out of the matrix, which requires overcoming the frictional bond between the fiber and the clay. This mechanism dissipates the energy of the crack and prevents it from widening. Additionally, the fibers bridge the cracks that do form, continuing to transmit tensile loads across the fracture plane. This allows the wall to retain its structural integrity even if minor shrinkage cracks appear. The longevity of wattle and daub structures, some medieval examples survive to this day, is due to the application of surface coatings. Once the daub had hardened, it was typically finished with a lime plaster or whitewash. This layer served a dual purpose. Mechanically, it provided a hard, sacrificial skin that protected the softer daub from impact and abrasion. Chemically, it acted as a semi-permeable membrane. Lime plaster is breathable, meaning it blocks the ingress of bulk liquid water, rain, while allowing water vapor to escape from within the wall. This is a critical property for earthen composites. If moisture were trapped inside the daub by an impermeable barrier, like modern cement or latex paint, the clay would soften and the organic timber reinforcement would rot. The ancient use of lime ensured that the composite system remained in equilibrium with its environment, absorbing and releasing humidity without degrading, a lesson in moisture management that modern building science has had to relearn. Harvested composite, straw, mud, and the physics of tensile strength. While Wattle and Daub utilized wood as a macro reinforcement, the use of straw in mud bricks represents the earliest application of micro reinforcement. This practice, famously referenced in the biblical account of the Israelites in Egypt, was not merely a ritual or a filler technique. It was a calibrated engineering decision based on the optimization of tensile properties in a brittle matrix. To understand the necessity of straw, one must first understand the failure mode of mud brick. Sun-dried earth is a material with high compressive strength. It can support the heavy vertical loads of a wall or a granary dome. However, it is inherently brittle and weak in tension. During the manufacturing process, as the brick dries in the sun, the differential drying rates between the surface and the core create significant tensile stresses. The surface dries and shrinks first, while the core remains wet and expanded. This differential pulls the surface apart, creating shrinkage cracks. In a structural context, these are fatal flaws. They act as stress concentrators. When the brick is loaded, stress accumulates at the tip of the crack, causing it to propagate through the brick and split it. The addition of straw alters this physical behavior at a fundamental level. The straw stalks are randomly oriented throughout the matrix, creating a three-dimensional fibrous network. Modern experimental archaeology and material science research have vindicated the ancient recipe. Studies investigating the mechanical properties of straw-reinforced clay have found that there is an optimal ratio of fiber to matrix. Research indicates that a straw content of approximately 1% to 1.5% by weight yields the maximum benefit. At this ratio, the straw provides sufficient bridging capacity to arrest shrinkage cracks without compromising the compressive density of the brick. The fibers effectively stitch the clay together. When the brick is subjected to bending or shear forces, such as those caused by ground settlement or thermal expansion, the straw fibers engage in tension, providing the brick with a degree of ductility. A plain mud brick fails suddenly and catastrophically. A straw-reinforced brick fails gradually, deforming before it breaks. Interestingly, research also shows that exceeding this optimal ratio can be detrimental. If too much straw is added, the fibers can clump together, creating voids and weak spots within the brick, where there is insufficient clay binder to hold the mass together. This balling effect reduces the overall compressive strength and increases water absorption, making the brick more susceptible to weathering. This implies that ancient brickmakers possessed a highly tuned empirical knowledge of mix design, strictly controlling the proportions of their composite to stay within the peak performance window. The synergy between mud and straw extends beyond simple mechanics into the realm of organic chemistry. When straw is mixed into wet mud and allowed to ferment, a process often depicted in ancient art where workers tread the mixture for days, it undergoes biological degradation. This decay process releases a variety of organic compounds, most notably humic acid and lactic acid. Humic acid acts as a deflocculant. In a clay suspension, clay particles tend to stick together in random flocculated clumps. A deflocculant neutralizes the electrical charges on the clay particles, causing them to repel each other and disperse more evenly throughout the water. This dispersion increases the plasticity and workability of the mud, allowing it to be molded more tightly and with less water. Less water means less shrinkage during drying, and therefore fewer cracks. Furthermore, the proteins and polysaccharides released by the decaying straw can act as natural glues, binding the clay particles more tightly upon drying. Thus, the ancient brick was not just a physical mixture of mud and grass, it was a biocomposite, where the reinforcement chemically modified the matrix to improve its processing properties and final strength. Biomechanical engine, the Mongol Composite Bow. If Wattle and Daub represents the static application of ancient composites, the Mongol bow represents its dynamic pinnacle. Emerging from the Eurasian steppe, this weapon is arguably the most complex mechanical device of the pre-industrial world. It is a recurve bow constructed from a laminate of 3 distinct biological materials: horn, wood, and sinew, each selected for its specific mechanical properties and combined to store and release energy with devastating efficiency. The design of the Mongol bow was a direct response to the environmental limitations of the steppe. Unlike medieval England, where long staves of elastic yew wood were available to make self-bows, the steppe offered few trees suitable for such construction. Mongol artisans turned instead to the materials of their herds: the horns of water buffalo or mountain sheep, and the tendons of deer or cattle. The bow was constructed as a sandwich structure, with each layer serving a distinct role in the storage of potential energy. The center of the laminate was a thin lath of wood or bamboo. In the composite system, the wood does not serve as the primary energy storage medium. Instead, it acts as the dimensionally stable chassis, or shear web, that separates the tension and compression layers. It gives the bow its shape and provides a surface for gluing. The belly of the bow, the side facing the archer, is subjected to intense compressive forces when the bow is drawn. Wood, particularly the short lengths available on the steppe, would crush or buckle under the compression required for a powerful bow. To solve this, artisans glued strips of horn to the belly. Horn is composed of keratin, a natural polymer. It has exceptional compressive strength and, crucially, a high coefficient of restitution. It can be compressed significantly without suffering permanent deformation or set, and springs back to its original shape instantly. The back of the bow, the side facing the target, is stretched when the bow is drawn. To withstand this tension, layers of sinew were applied. Sinew, derived from animal tendons, is almost pure collagen. It is nature's high tensile fiber. When processed and glued to the bow, sinew acts like a powerful biological rubber band. It can stretch significantly without breaking and snaps back with tremendous force. The true genius of the Mongol bow lay in how these materials allowed for a radical geometry, the reflex. A wooden longbow is straight when unstrung. A Mongol composite bow, however, forms a C shape when unstrung, curling forward in the opposite direction of the draw. To string the bow, the archer must bend the limbs back against this natural reflex. This action pre-tensions the composite structure. The sinew on the back is already stretched, and the horn on the belly is already compressed, even before the arrow is nocked. When the bow is finally drawn, the energy storage is immense. The force draw curve of a composite bow is much steeper and fuller than that of a longbow, meaning it stores more energy per inch of draw. This allowed the Mongol bow to be short enough for use from horseback while delivering the kinetic energy of a much larger infantry weapon. The bow also featured stiff tips known as sias, or ears. These acted as levers, providing a mechanical advantage at the end of the draw. They effectively lengthened the limb as the string angle became acute, smoothing the draw and allowing the archer to manage high draw weights, often exceeding 100 pounds, with greater control. The structural integrity of this laminate depended entirely on the adhesive. A delamination in battle would be fatal. The Mongols utilized animal glues, specifically fish glue made from the swim bladders of sturgeon or other fish. Fish glue was prized over hide glue for its superior elasticity and adhesive strength. A rigid glue would crack under repeated flexing of the bow limbs. Fish glue remained flexible enough to bend with the materials while maintaining a bond stronger than the materials themselves. The manufacturing process was chemically delicate. The glue had to be heated to a precise temperature. Too hot, and the protein chains would break down, denature. Too cool, and it would gel before penetrating the fibers. The assembly of a bow was a slow, rhythmic process that could take a year or more. The sinew was applied in thin layers, with each layer allowed to dry and cure for weeks. This slow curing process was essentially a primitive form of polymer curing, resulting in a unified biocomposite structure where the layers were indistinguishable from one another. Geometry of scarcity. Ancient Egyptian plywood. While the Mongols sought power through composites, the ancient Egyptians sought efficiency. The Nile Valley is rich in stone and mud, but poor in quality timber. Native trees like the acacia and sycamore fig are knotty, irregular, and rarely produce long, straight planks. Importing cedar from Lebanon was an expensive royal luxury. To construct the large, flat panels required for sarcophagi and shrine furniture, Egyptian carpenters invented a technique that predates modern industrial plywood by over 4 millennia: the cross-laminated veneer. The most striking evidence of this technology is a coffin dating to the 3rd dynasty, circa 2600 BCE, discovered in the step pyramid complex of Djoser at Saqqara. This artifact challenges the modern assumption that plywood is a 20th century industrial product. Archaeological analysis reveals that the coffin's sides were not solid planks, but composite panels constructed from 6 layers of wood veneer, each approximately 4 millimeters thick. Crucially, the Egyptians employed the defining principle of modern plywood: cross-graining. They alternated the direction of the grain in each subsequent layer, vertical, then horizontal, then vertical again. This was not a decorative choice, it was a profound engineering insight into the anisotropic nature of wood. Wood is strong and stable along the grain, longitudinally, but weak and unstable across the grain, tangentially or radially. It expands and contracts significantly with changes in humidity across its width. If the Egyptians had simply glued layers with the grain running parallel, the panel would have warped, twisted, or split as the wood moved. By crossing the grains, they mechanically locked the dimensions of the panel. The expansion of one layer was restricted by the longitudinal stiffness of the adjacent layer. This created a panel that was isotropic in the plane, equally strong and stable in all directions. The production of these veneers without industrial machinery was a testament to the skill of Egyptian carpenters. They used copper pole saws to slice logs into thin sheets. Since copper is a relatively soft metal, this required frequent sharpening and the use of abrasive sand to aid the cutting action. Once the veneers were cut, they were assembled into the composite panel. Unlike the chemical bonding of the Mongol bow, the Egyptian plywood relied heavily on mechanical fixation. The layers were pinned together using thousands of tiny wooden dowels or pegs. This sewn wood technique created a mechanical interlock between the layers. While animal glues, casein, or hide glue were likely used to assist the bond, the arid climate of Egypt can cause glues to become desiccated and brittle over centuries. The wooden dowels ensured that the ply structure remained intact even if the adhesive failed. This technology allowed the Egyptians to maximize their scarce timber resources. High-quality imported woods could be used for the visible exterior veneers, while lower-quality local woods could be hidden in the core layers. a practice of veneering that remains a standard in furniture making today. Synthetic matrix, the 19th and early 20th century transition. For thousands of years, composite materials relied on natural matrices, mud, pitch, or animal glues. The transition to the modern era of composites began with the chemical synthesis of the matrix itself. This shift moved material science from the realm of found ingredients to designed molecules, a revolution spearheaded by the invention of phenolic resins. The pivotal moment in this transition occurred in 1907 with the work of Leo Baekeland, a Belgian-American chemist. Baekeland was searching for a synthetic replacement for shellac, a natural resin secreted by the lac beetle, which was in high demand for the expanding electrical industry. His research focused on the reaction between phenol, a coal tar derivative, and formaldehyde. Chemists had known that these two chemicals produced a sticky resinous substance, but it was notoriously difficult to control. It would often foam up or harden into an unusable mass. Baekeland's genius was the invention of a pressure vessel, the Baekelizer, which allowed him to control the heat and pressure of the reaction precisely. This enabled him to stop the polymerization process at an intermediate stage, creating a resin that could be molded and then hardened permanently. The resulting material, polyoxybenzyl methylene glycol anhydride, or Bakelite, was the world's first fully synthetic thermosetting plastic. Unlike thermoplastics, which can be melted and reformed, Bakelite formed a permanent cross-linked molecular structure that was heat-resistant, chemically inert, and electrically non-conductive. However, pure Bakelite resin had a major flaw. It was brittle. Like the mud of the ancients, the cured resin was susceptible to cracking under impact. To solve this, Baekeland applied the ancient principle of the composite. He added a reinforcement. The filler of choice was wood flour, finely ground wood particles, similar to sawdust, but sieved to a uniform flour-like consistency. The addition of wood flour was not merely an economic measure to bulk up the expensive resin, it served a critical mechanical function. The wood particles acted as crack arresters within the phenolic matrix, interrupting the propagation of fractures and absorbing impact energy. This composite material, phenolic resin reinforced with wood flour, was the defining structural material of the early 20th century. It possessed high impact strength, excellent electrical insulating properties, and the ability to be molded into complex shapes with high precision. It was used for everything from the distributor caps of the internal combustion engine to the casings of the new telephone and radio networks. This development marked the industrialization of the composite concept. No longer was the composite a unique, handcrafted artifact like the Mongol bow. It was now a standardized industrial commodity, with the matrix and reinforcement ratio strictly controlled to produce consistent mechanical properties. Glass Revolution, World War II, and the birth of fiberglass. While Bakelite demonstrated the potential of synthetic matrices, its reinforcement, wood flour, was particulate and relatively low strength. The leap to modern high-performance composites required a fibrous reinforcement that exceeded the strength of steel. This arrived with the invention of mass-produced glass fiber and its marriage to polyester resin during the crisis of the Second World War. Glass fibers had existed as a curiosity for centuries. Venetian glassblowers had spun decorative strands, but they were impossible to produce in useful commercial quantities. This changed in 1932 at the Owens, Illinois Glass Company. A researcher named Games Slater was experimenting with glass manufacturing when a jet of compressed air accidentally struck a stream of molten glass. Instead of ruining the batch, the air blast atomized the glass into a shower of fine, continuous fibers. This accident laid the foundation for mass production of fiberglass. Slater and his team refined the process, and in 1938, Owens, Illinois Glass Company and Corning Glass Works merged their research divisions to form the Owens-Corning Fiberglass Corporation. Initially, these fibers were viewed as a superior form of insulation, glass wool, or filtration media. However, engineers recognized the potential. Individual glass fibers possess immense tensile strength. If they could be woven into a cloth and embedded in a plastic resin, the result would be a material with the strength of metal but a fraction of the weight, and crucially, immune to rust. The challenge lay in finding a suitable matrix. Phenolic resins, like Bakelite, required high pressure and heat to cure, necessitating heavy steel molds. This made them unsuitable for producing large, complex structures like boat hulls or aircraft fuselages. The breakthrough came with the development of polyester resin. In 1936, Carlton Ellis of DuPont patented a polyester resin, but early versions were unstable and difficult to cure reliably. The critical advance arrived in 1942, spurred by wartime demands. American Cyanamid produced Laminac, a polyester resin formulation that could cure at room temperature or with low heat without the need for high pressure. This development was the catalyst for the modern composites industry. Now, engineers could take soft, flexible layers of Owens-Corning glass cloth, drape them over a simple, inexpensive mold made of wood, plaster, or cement, saturate them with American Cyanamid's liquid polyester resin, and let them harden into a rigid structural part. This process, known as contact molding or wet layup, democratized composite manufacturing, moving it from the heavy industrial press to the workshop floor. Garage and the laboratory, the first applications of GFRP. The convergence of glass fiber and polyester resin found its first applications in two very different environments: the garage of a boat builder in Ohio and the top-secret laboratories of MIT. One of the first visionaries to combine these technologies was Ray Green, a Toledo-based engineer who had worked with Owens-Corning during his university days. Green was intimately familiar with the properties of glass fiber. In 1942, obtaining a shipment of the newly available polyester resin from American Cyanamid and glass fabric from Owens-Corning, he set out to prove that this new material could revolutionize naval architecture. Green produced a composite boat, likely a Snipe-class sailboat or a small dinghy. This vessel is widely considered the first polyester fiberglass composite boat in history. The significance of this experiment was the manufacturing method. Green did not have a factory. He cured his early prototype in a homemade autoclave, essentially a box equipped with heaters, in his own garage. This proved that high-strength composite structures could be fabricated without the massive capital investment required for metalworking. It demonstrated that fiberglass was rot-proof, leak-proof, and could be molded into seamless hydrodynamic shapes that were impossible with wooden planks. Although the war interrupted civilian production, Green's 1942 experiment birthed the marine composites industry that would explode in the 1950s. While Green worked in his garage, a more urgent development was taking place at the Radiation Laboratory, or RAD Lab, at the Massachusetts Institute of Technology. The Allies had developed radar, a decisive technology for detecting enemy aircraft and U-boats. However, radar antennas were fragile, rotating mechanisms that needed to be mounted on the exterior of aircraft. They required a cover, a radome, to protect them from the 300-mile-per-hour airstream, ice, and freezing rain. This presented a paradox. The cover had to be structurally strong enough to withstand aerodynamic loads, but electrically invisible to radio waves. Aluminum was strong but opaque to radar. It would block the signal like a mirror. Plywood, the initial choice, was problematic. Wood absorbs moisture. Water has a high dielectric constant. When a plywood radome got wet or icy, it would attenuate the radar signal, rendering the system blind or distorting the beam. The solution was glass fiber reinforced polymer, GFRP. Glass is an electrical insulator with a low, stable dielectric constant. When embedded in polyester resin, it created a waterproof, strong, and RF transparent shield. Scientists at the RAD Lab, working on systems like the SCR-584 ground radar and the Eagle ANPQ-7 airborne radar for the B-29 Superfortress, developed the sandwich radome construction. This design, known as the A-sandwich, consisted of two thin skins of high-density fiberglass separated by a thick, low-density core, often a cellular honeycomb or foam. This configuration provided immense stiffness-to-weight ratio and minimized radar reflection. By 1944, fiberglass radomes were standard equipment on Allied aircraft, such as the B-29 and the night fighter variants of the de Havilland Mosquito, which used a fiberglass thimble radome to house its intercept radar. These radomes protected the sensory organs of the Allied war machine, allowing for precision bombing through clouds and the detection of submarines in the Atlantic. This military application proved the viability of high-performance composites under the most extreme conditions, validating the technology that would soon build the corvettes, Eames chairs, and surfboards of the post-war era. Advanced Composites, 1950 to present future. The history of technological civilization is inextricably bound to the materials available to its engineers. From the stone tools that defined early hominids to the iron and steel that forged the Industrial Revolution, the limits of human capability have often been the limits of material science. By the mid-20th century, the dominant materials, steel, aluminum, and titanium, were reaching their asymptotic performance limits. The dawn of the jet age and the burgeoning space race presented a new set of physical challenges that monolithic metals could not efficiently solve. Aircraft needed to fly faster and higher, requiring structures that were stiff enough to prevent aeroelastic flutter, yet light enough to carry useful payloads. Rocket nozzles needed to withstand temperatures that would melt conventional alloys. The weight wall became the primary adversary of aerospace engineering. Into this breach emerged the era of advanced composites. Unlike the rudimentary composites of antiquity, such as straw-reinforced mud bricks or the early 20th century phenolic laminates like Bakelite, advanced composites represented a paradigm shift. They were defined by the deliberate engineering of a material system where high-performance fibers possessing exceptional specific strength and stiffness were embedded within a matrix material that transferred loads and protected the fibers. This synergy created a material that was superior to its individual constituents, capable of tailored anisotropy, where strength could be directed exactly where it was needed. The evolution of these materials, from the laboratory curiosities of the 1950s to the ubiquitous structural backbones of modern airliners like the Boeing 787, is a saga of chemical ingenuity, geopolitical rivalry, and relentless industrial optimization. It is a story that traverses the high-stakes environment of the Cold War, where cost was secondary to performance, to the commercial realities of the 21st century, where sustainability and high-rate manufacturing dominate the discourse. This provides an exhaustive analysis of this evolution, tracing the trajectory of carbon fibers, aramids, and diverse matrix systems from their post-World War II origins to their future applications in urban air mobility and beyond. Precursors, theoretical potential, and early filamentation. While the age of advanced composites is generally demarcated by the post-World War II era, the fundamental concept of carbon filaments predates the modern aerospace industry by nearly a century. The intellectual lineage of carbon fiber begins in the unlikely setting of Victorian lighting research. In 1879, Thomas Edison, in his relentless pursuit of a durable incandescent light bulb, turned to carbonization. He baked cotton threads and bamboo slivers at high temperatures in an oxygen-free environment, a process known as pyrolysis. These early carbon filaments were successful in conducting electricity and withstanding the heat of incandescence, but their mechanical properties were poor. They were brittle and lacked the organized molecular structure required for tensile strength. When tungsten filaments were introduced in the early 1900s, offering superior durability and luminosity, carbon fiber was effectively rendered obsolete. For the next 50 years, carbon fiber remained a dormant technology, a footnote in the history of electrical engineering rather than a chapter in structural mechanics. The theoretical resurrection of fibrous materials was driven by the physics of fracture mechanics. In the 1920s, A. Griffith proposed that the strength of a material is limited by the presence of microscopic flaws or cracks. He theorized that if a material could be made small enough, specifically thin enough, the probability of a critical flaw existing within it would diminish significantly. This led to the concept of whiskers, single crystals of material that were virtually flaw-free and exhibited strength approaching the theoretical limits of atomic bonding. By the 1950s, this theory began to intersect with the practical needs of the U.S. military. The advent of intercontinental ballistic missiles, ICBMs, and high-performance jet aircraft created a desperate need for materials that could survive extreme thermal and mechanical environments. Fiberglass, the standard composite of the World War II era, was insufficient for the re-entry temperatures of missile warheads or the exit cones of rocket nozzles. The U.S. Air Force needed something better. Carbon fiber revolution, 1960s to 1980s. The birth of the modern carbon fiber industry was not a singular event, but a bifurcated development occurring simultaneously in the United States, Japan, and the United Kingdom. Each region pursued different precursor materials, rayon, polyacrylonitrile, PAN, and pitch, driven by differing industrial capabilities and strategic priorities. In 1956, Union Carbide opened its Parma Technical Center in Cleveland, Ohio, a facility that would become the crucible of American carbon fiber research. Dr. Roger Bacon, a physicist at the center, was conducting fundamental research on the triple point of carbon, the temperature and pressure at which carbon exists simultaneously as solid, liquid, and gas. In 1958, during an experiment with a high-pressure arc furnace, Bacon observed the formation of graphite whiskers on the negative electrode. These whiskers were a revelation. They were perfect graphite crystals with a tensile strength of 20 gigapascals GPa and a Young's modulus of 700 GPa. They were the strongest and stiffest material for their weight ever produced by humanity. However, they were also microscopic and astronomically expensive to produce, estimated at millions of dollars per pound. While Bacon's discovery proved the theoretical upper limits of carbon's performance, it did not immediately solve the engineering problem of mass production. To create a commercially viable fiber, Union Carbide turned to rayon, a cellulose-based polymer derived from wood pulp. By heat-treating rayon cloth, they produced the first advanced composites for the U.S. Air Force in 1958. These carbonized rayon fabrics were used as ablative reinforcements in rocket nozzle exit cones and re-entry heat shields. The material worked by slowly burning away, ablating during re-entry, carrying heat away from the warhead. However, the rayon process was plagued by profound inefficiencies. The carbon yield was pitifully low. Only about 20% of the initial rayon mass remained as carbon after pyrolysis. The molecular structure of rayon also collapsed during heating, making it difficult to align the graphite planes for high stiffness. Despite these drawbacks, the exigencies of the Cold War kept the rayon process alive. In 1964, Union Carbide scientists Bacon and Wesley Shalom developed a hot stretching process, stretching the carbon yarn at temperatures exceeding 2,800 degrees Celsius to orient the graphite layers. This produced high modulus fibers, but the cost remained prohibitive, leading engineers to nickname the material unobtainium. While the US struggled with rayon, a more efficient precursor was being investigated in Japan and the UK. In Japan, Dr. Akio Shindo of the Government Industrial Research Institute in Osaka began experimenting with polyacrylonitrile in the early 1960s. PAN, a synthetic polymer used in the textile industry, had a carbon backbone that was more conducive to carbonization. Shindo's process yielded a carbon recovery of nearly 55%, more than double that of rayon. This economic advantage was the first step toward commercial viability. The critical leap in performance, however, occurred in the United Kingdom. Researchers Watt, L.N. Phillips, and W. Johnson at the Royal Aircraft Establishment in Farnborough, UK, made a serendipitous discovery in 1963. They found that by oxidizing the PAN fiber in air while under tension, literally stretching it before the carbonization phase, they could prevent the polymer chains from relaxing. This stabilization step locked the molecular orientation in place. When the fiber was subsequently carbonized at high temperatures, the graphite planes formed in alignment with the fiber axis. This molecular orientation was the holy grail. It conferred immense stiffness, modulus, to the fiber, transforming it from a mere thermal insulator into a structural reinforcement capable of competing with metals. The RAE patented this process, and the British National Research Development Corporation, NRDC, licensed it to 3 UK companies, Rolls-Royce, Morganite, and Courtaulds. Rolls-Royce, eager to gain a technological edge in the fiercely competitive jet engine market, bet the company on this new material. They developed a composite material named high-fill, carbon fiber reinforced resin, and designed it into the fan blades of the RB210-1 engine. The promise was enticing. Lighter fan blades meant less centrifugal force, allowing for a lighter hub and casing, resulting in a dramatic reduction in engine weight and a leap in fuel efficiency. However, the transition from laboratory sample to rotating machinery is fraught with peril. In the late 1960s, during certification testing, the high-fill blades failed the critical bird strike test. When impacted by gelatin birds at takeoff speeds, the brittle carbon fibers shattered, destroying the engine's integrity. The lack of damage tolerance in these early composites was a catastrophic oversight. The failure of the high-fill blades forced Rolls-Royce to revert to titanium blades, adding weight and cost that contributed to the company's bankruptcy and nationalization in 1971. This high-profile failure sent a shockwave through the industry. It highlighted a fundamental dichotomy in composites, the trade-off between stiffness, modulus, and toughness, impact resistance. It would take decades of matrix toughening and hybridization to fully resolve this issue for air engines. Despite the setback at Rolls-Royce, the U.S. military pushed forward. The operational requirements of the Vietnam War and the strategic standoff with the Soviet Union demanded aircraft with unprecedented performance. The 1960s and 70s were the era of variable geometry, or swing-wing aircraft, designed to optimize aerodynamic performance at both low and high speeds. The General Dynamics F-111 Aardvark was the pioneer of this configuration. The immense structural loads placed on the wing pivot box and the tail surfaces at supersonic speeds created a nightmare for metallurgists. To solve the stiffness problem, the industry initially turned not to carbon, but to boron. Boron fiber, developed in the US by depositing boron vapor onto a fine tungsten wire, was the first true advanced composite to see service. It was incredibly stiff and had high compressive strength. The Grumman F-14 Tomcat, the U.S. Navy's fleet defender, utilized boron and epoxy composites for the skins of its horizontal stabilizers, ailerons. The F-14's tail needed to remain rigid during high-G maneuvers to maintain control authority. A metal tail would have suffered from aeroelastic flutter. Boron solved this. Similarly, the McDonnell Douglas F-15 Eagle employed boron composites for its empennage skins and rudder. Boron served as a bridge technology. It proved that fiber-reinforced polymers could survive the harsh environment of carrier landings and Mach 2 flight. However, boron had significant limitations. The tungsten core made the fibers thick, approximately 100 to 140 microns, restricting the radius around which they could be draped. They were also difficult to machine, diamond tools were required, and exorbitantly expensive. As the 1970s progressed, the PAN-based carbon fiber process matured. Union Carbide, recognizing the superiority of PAN, licensed the technology from Toray Industries in Japan in 1970. The cost of carbon fiber began to drop from the stratospheric $400 per pound levels, while its handling characteristics, thinner, flexible fibers, made it easier to manufacture complex shapes. By the advent of the F-16 Fighting Falcon and the FA-18 Hornet, carbon fiber had largely displaced boron as the primary composite material for military airframes. The economics of the carbon fiber industry in the 1970s and 80s were distorted by the war economy. The DoD was the primary consumer, and performance was the only metric that mattered. This led to a massive expansion of production capacity in the US, Japan, and Europe, predicated on the assumption of endless military growth. The fall of the Berlin Wall and the collapse of the Soviet Union in roughly 1990 shattered this paradigm. The peace dividend resulted in the cancellation or scaling back of major aerospace programs. DoD usage of carbon fiber plummeted by 60% between 1989 and 1990. The industry faced an existential crisis of overcapacity. However, this crash forced a necessary evolution. To survive, carbon fiber manufacturers had to find civilian markets. They pivoted aggressively to sporting goods. Golf club shafts, tennis rackets, and fishing rods became the lifeblood of the industry in the early 1990s. While less glamorous than fighter jets, these high-volume consumer goods provided the cash flow needed to sustain R&D and manufacturing infrastructure. They also familiarized the general public with graphite and carbon fiber as premium materials, laying the brand groundwork for the automotive and commercial aerospace adoption that would follow. Aramid achievement, toughness, and ballistics. While carbon fiber was conquering the domain of stiffness, another revolution was occurring in the domain of tensile strength and toughness. The protagonist of this story was Stephanie Kwolek, a chemist at DuPont's pioneering laboratory. In 1965, Kwolek was searching for strong, lightweight fibers to reinforce tires, anticipating a gasoline shortage. She was working with poly-P-phenylene terephthalamide, a rigid rod polymer. During her experiments, she produced a solution that was unlike any she had seen before. It was cloudy, opalescent, and had low viscosity. Standard operating procedure would have been to discard such a solution as contaminated or polymerized incorrectly. Kwolek, demonstrating the intuition of a master scientist, insisted on spinning it. The resulting fiber was startling. It possessed a tensile strength 5 times that of steel on a weight-for-weight basis. The polymer chains in the fiber were highly oriented and rigid, acting like bundled rods. DuPont trademarked this material as Kevlar. While Kevlar is most famous for bulletproof vests, its impact on aerospace safety was profound. The defining application was the engine containment ring. In a high-bypass turbofan engine, the fan blades are massive components rotating at high velocities. If a blade were to detach due to fatigue or foreign object damage, FOD, the kinetic energy released is enormous. The engine casing must contain this liberated blade to prevent it from penetrating the fuselage. Traditionally, these containment rings were made of heavy steel. Kevlar offered a revolutionary alternative. By wrapping layers of dry Kevlar fabric around the engine casing, engineers created a containment system that acted like a catcher's mitt. When a blade struck the casing, the Kevlar fabric would deform, absorbing the kinetic energy through fiber strain and friction, preventing penetration. This system was significantly lighter than steel, contributing to the overall weight reduction of the engine and the aircraft. Kevlar also became the standard material for aircraft cargo liners. The walls of a cargo hold are subjected to constant abuse from loading equipment and luggage. They must be puncture-resistant and, crucially, fire-resistant. Kevlar phenolic laminates provided a tough, lightweight barrier that protected the aircraft's primary structure from internal damage and effectively contained fires within the cargo hold. Diversification of matrix materials, high-heat environments. The limitation of both carbon epoxy and Kevlar epoxy was temperature. Polymer matrices generally degrade at temperatures above 150 degrees Celsius to 200 degrees Celsius. For the hot sections of aerospace vehicles, jet engines, hypersonic leading edges, and missile exhaust cones, engineers needed composites that could survive fire. This drove the development of metal matrix composites, or MMCs, and ceramic matrix composites, or CMCs. MMCs embed high-strength fibers within a light metal alloy, typically aluminum, titanium, or magnesium. This combination yields a material with the conductivity and ductility of metal, but the stiffness and strength of the fiber, usable at temperatures where polymers would melt. One of the most prominent uses of MMCs was in the space shuttle. The orbiter's mid-fuselage, the structural backbone spanning the payload bay, required struts that were light, stiff, and thermally stable. General Dynamics utilized boron aluminum tubes for this application. These struts, composed of boron fibers diffusion bonded into an aluminum matrix, provided a 44% weight savings, approximately 320 pounds, compared to conventional aluminum extrusions. Crucially, the boron aluminum material had lower thermal conductivity, reducing the insulation requirements for the shuttle structure. MMCs also solved a critical dynamic problem on the F-16 Fighting Falcon. The aircraft features two ventral fins beneath the tail for stability. Early flight tests revealed that these fins suffered from severe aerodynamic buffeting. They vibrated violently during certain maneuvers, leading to rapid fatigue failure of the aluminum structure. Instead of redesigning the aerodynamics, engineers changed the material. They replaced the aluminum fins with aluminum reinforced with silicon carbide particles. This MMC was significantly stiffer, which shifted the natural frequency of the fins away from the buffeting frequency, effectively detuning the resonance. The service life of the fins increased from hundreds of hours to thousands. In the Trident missile system, MMCs were used for the guidance system instrument covers. Inertial navigation systems rely on the precise alignment of gyroscopes and accelerometers. Any thermal warping of the structure degrades accuracy. MMCs offered the high stiffness and low coefficient of thermal expansion, CTE, necessary to maintain instrument-grade stability during the missile's flight. The ultimate frontier for composites was the interior of the jet engine turbine, where temperatures exceed the melting point of most metals, above 1300 degrees Celsius. Ceramics like silicon carbide can withstand this heat, but they are inherently brittle. A monolithic ceramic part will shatter under thermal shock or impact. The development of CMCs, ceramic fibers in a ceramic matrix, was met with intense skepticism. A 2001 Institute for Defense Analyses report notoriously questioned the viability of CMCs with the headline, "Will pigs fly before ceramics do?" The report highlighted the immense manufacturing costs and the risk of catastrophic brittle failure. General Electric Aviation spent decades and billions of dollars proving the skeptics wrong. Their focus was silicon carbide and silicon carbide composites. The mechanism that makes CMCs viable is crack bridging. When the ceramic matrix cracks under stress, the fibers span the crack, holding the material together and allowing it to carry load even when damaged. This gives the ceramic a pseudo-ductility. The entry into the commercial fray was the CFM LEAP engine. GE introduced CMC shrouds in the high-pressure turbine section. These components operate without the complex air cooling channels required for metal parts. By reducing the need for cooling air, which is bled from the compressor and bypasses the combustion cycle, the engine's thermodynamic efficiency is increased. The CMC parts are also 1/3 the weight of the nickel superalloys they replaced. The LEAP engine's success validated CMCs, leading to expanded use in the GE9X engine, which features CMC combustor liners and nozzles. Modern era, 2000s to present, standardization and nanotechnology. The turn of the millennium marked the transition of composites from exotic to standard. The Boeing 787 Dreamliner, introduced in 2004 and entering service in 2011, became the first major commercial airliner to feature a fuselage and wing structure made primarily of carbon fiber reinforced polymer, or GFRP. The 787 represents the industrial maturity of the pan-carbon revolution started by the RAE 40 years prior. The aircraft is 50% composite by weight. The fuselage is manufactured not as panels riveted together, but as single, continuous barrel sections wound on massive mandrels. This eliminates thousands of fasteners, reducing aerodynamic drag and manufacturing assembly time. Beyond fuel efficiency, 20% better than the 767 it replaced, the composite fuselage transformed the passenger experience. Composites do not corrode like aluminum. This allowed Boeing to increase the cabin humidity and pressure, simulating an altitude of 6,000 feet instead of 8,000 feet, reducing passenger fatigue and dehydration. Operational data has been flawless. With over 700 aircraft in service, maintenance checks have shown zero fatigue issues in the composite structure, a stark contrast to the fatigue-prone metal airframes of the past. As macro composites reached maturity, research zoomed in to the nanoscale. Carbon nanotubes and graphene promised theoretical strengths orders of magnitude higher than conventional fibers. One of the first practical applications of CNTs in deep space was on NASA's Juno mission to Jupiter. The spacecraft's environment is dominated by intense radiation belts that can cause electrostatic discharge, or ESD, sparks that can fry electronics. Traditional spacecraft use heavy aluminum foil to ground the structure. Juno utilized CNT-infused composite face sheets and engine covers. The conductive network of nanotubes within the resin provided a built-in ESD pathway, protecting the spacecraft without the weight penalty of metal shielding. In the military domain, nanocomposites have enabled robust stealth. The Lockheed Martin F-35 Lightning II utilizes a fiber mat skin enhanced with nanocomposites. Unlike the F-117 or B-2, which relied on fragile radar-absorbent coatings that required constant maintenance, the F-35's radar-absorbing properties are integrated into the structural skin itself. This conductive skin is durable, repairable, and maintains its stealth profile even after exposure to harsh maritime environments. Research has also shown that adding small amounts of graphene, 0.075% by weight, to the pan precursor or the carbon fiber sizing can significantly enhance properties. Graphene reduces the porosity of the carbon fiber during manufacturing, resulting in a 225% increase in strength and a 184% increase in modulus in experimental fibers. This technology offers a pathway to lower-cost carbon fiber, targeting $5 per pound, by allowing for faster, cheaper production processes without sacrificing performance. The ubiquity of composites has created a new problem: waste. Thermoset composites, once cured, are difficult to recycle. They cannot be melted down. This has driven the industry toward green composites and circular economy solutions. Boeing's Eco-Demonstrator program has pioneered the use of flax fibers combined with bioresins for aircraft interiors. Flax, a natural fiber, offers excellent vibration damping, better than carbon or glass, making it ideal for acoustic panels and sidewalls. By using a resin derived from 25% bio content, Boeing aims to reduce the life cycle carbon footprint of the cabin interiors. These materials are not structural in the primary sense, but they reduce weight and rely on renewable feedstocks. To address the waste from carbon fiber manufacturing, Boeing partnered with ELG Carbon Fiber UK. ELG developed a pyrolysis process to reclaim carbon fibers from cured composite scrap, such as trimmings from the 777X wing center. The resin is burned off in an oxygen-free oven, leaving the carbon fibers intact. While these reclaimed fibers lose their continuous length, becoming chopped or milled, they retain much of their stiffness and are sold into the automotive and electronics industries for use in injection molding. This partnership has diverted millions of pounds of high-value carbon from landfills, closing the loop on the material life cycle. Future projections: urban air mobility and thermoplastics. The next great leap in composites is being driven by urban air mobility, UAM, the emerging market of electric vertical takeoff and landing eVTOL aircraft, or air taxis. Companies like Joby Aviation and Archer Aviation aim to manufacture thousands of aircraft per year, a rate closer to the automotive industry than traditional aerospace. The curing times of thermoset composites, hours in an autoclave, are a bottleneck that makes this impossible. The industry is shifting toward thermoplastic composites, using matrices like PEEK, PEEK, or PA6. Unlike thermosets, thermoplastics can be melted and resolidified indefinitely. This allows for rapid cycle times. Parts can be stamped or compression molded in minutes. Components can be joined via ultrasonic or induction welding, eliminating rivets and adhesives, which reduces weight and assembly time. Thermoplastics are inherently tougher and more impact-resistant than brittle epoxies. Joby Aviation has partnered with Toray Advanced Composites to certify thermoplastic materials for their eVTOL aircraft. Archer Aviation has similarly engaged Hexel and FACC to establish a supply chain capable of high-rate composite production. The ability to produce aerospace-grade structures at automotive speeds is the key enabler for the democratization of flight. The age of advanced composites has been a journey from the impossible to the routine. It began with the physics of whiskers and the desperate needs of the Cold War, birthing materials like carbon and boron that allowed engineers to defy the weight wall. It matured through the resilience of Kevlar and the thermal mastery of CMCs, proving that polymers and ceramics could survive where metals failed. Today, as we stand on the cusp of the UAM revolution, the focus has shifted from pure performance to processability and sustainability. The advanced composites of the future will not only be stronger and lighter, they will be recyclable, bio-derived, and manufactured at speeds that Thomas Edison, baking his bamboo threads in 1879, could simply never have imagined.